So hello everyone again. We are back and still continuing our studies of intermolecular forces. So in this lecture, our focus is going to be on how intermolecular forces have an effect on the physical states of matter. And the types of matter we're looking at here are covalent compounds and molecular elements. In addition to seeing how intermolecular forces affect physical states, we're also going to take a look at how they have an effect on phase changes, also known as changes of state. So let's begin at the beginning and note something very important. And that is this, that when intermolecular forces are stronger, they pull the molecules of a substance closer together. So strong intermolecular forces, those are the attractions between molecules. If they're stronger, the molecules get pulled closer together. Well, let's remember the main difference between a solid, liquid, and a gas are how far apart the molecules are. So if we think about a gas, so gases, well, are the particles in a gas close together or far apart? Well, of course, we know that particles of a gas are spread out very far apart. So we know that the molecules are very far apart. As opposed to saying compared gases to liquids and solids. And in both liquids and solids, the molecules are much closer together. Now, they're a little bit closer together in solids than liquids, but there's not a huge difference in the closeness of the molecules of a liquid versus those of a solid. So I'm going to put liquids and solids together. So liquids and solids, in contrast to our gases, have molecules that are much closer together. So let's write that here. Molecules are much closer together. So what can we conclude? Well, the only way that the molecules are much closer together in liquids and solids has to be due to their IMFs. It's the IMFs that are pulling them together. And so we can fairly conclude that the IMFs in liquids and solids are stronger, considerably stronger, in fact, than the IMFs in gases. And this will always be the case. In naturally occurring gases, they have weak IMFs. Naturally occurring liquids and solids have considerably stronger intermolecular forces. And by the way, when I say naturally occurring, I mean the physical state at room temperature and room pressure, which in fact is what we're going to deal with in our second ice problem. So our second ice question over here for chapter 10 is going to explore this topic. Which substance in each pair is more likely to occur naturally at room temperature and pressure as a gas? Okay, so the first two are in the first line over here. It's CH3F and CH3OH. CH3F is a compound called fluoromethane. And well, we've already met CH3OH, that's our old friend methanol. So the place to begin is to determine what type of intermolecular forces we're dealing with in each substance, and then how strong the intermolecular forces are. So let's take fluoromethane off to the left. Well, fluoromethane is clearly a polar substance, as is methanol. Methanol on the right is polar, but note that methanol has this very special OH bond, which makes methanol superpolar. Now, being superpolar tells us that the types of intermolecular forces we find between methanol molecules are hydrogen bonding intermolecular forces and London dispersion intermolecular forces. Over in polar fluoromethane, however, we're going to have dipole-dipole intermolecular forces as well as London dispersion. London dispersion shows up in everything you might remember. Now, before we decide which of these intermolecular forces are stronger, we do need to ask ourselves a question about the molar masses of these two substances. Because if the molar masses are similar, we can then do a comparison of the strengths of these IMFs. Well, it turns out that the molar mass of fluoromethane, and I'm just going to give us an approximate value. Fluoromethane's molar mass is approximately 34 grams per mole. Meanwhile, methanol over here on this side has an approximate molar mass of 32 grams per mole. So that little squiggly thing is not an equals, it's an approximately equals. Now, 34 grams per mole, 32 grams per mole means that these two substances have very similar molar masses. So I'm going to write that here, similar molar masses. And if the molar masses are similar, it tells us that we can then do a direct comparison of their IMFs. And we know that for similar molar masses, hydrogen bonding is always stronger than dipole-dipole intermolecular forces. And so we expect here to have stronger IMFs for methanol and comparatively weaker intermolecular forces for fluoromethane. Now, the problem is asking us to identify which of these is most likely to occur as a gas. So a gas would have weaker intermolecular forces. And therefore, if we have to choose between these two, well, our choice would be clear, that fluoromethane would most likely occur as a gas, which it does at room temperature and pressure. And in point of fact, methanol, which is our other substance, naturally occurs as a liquid at room temperature and pressure. That's its actual state. Okay, that wasn't so bad. Now let's do it for the next two substances, which is iodine, I2, diatomic I2, and our old friend carbon dioxide. So once again, let's start by identifying whether they're polar or nonpolar to get their IMFs right. Well, as it turns out, we've already seen that carbon dioxide is nonpolar. Meanwhile, I2 is also nonpolar. It's the same element bonded. All right, so then it's got to be nonpolar. There's nothing else it could be. And being both nonpolar, the only intermolecular forces that both of these substances experience are London dispersion forces only. Now, at this point, we might say, uh-oh, what do we do? They're both London dispersion forces. But then we're going to remember that London dispersion force strength increases as molar mass increases. So now let's check out the molar masses of these two substances. Well, the molar mass of carbon dioxide is roughly 44 grams per mole. Meanwhile, the molar mass of iodine is approximately 254 grams per mole. So these are not similar molar masses. And here we're going to remember, if molar mass goes up, IMF strength goes up as well. So there's a correlation. And so in this particular example, we expect that iodine with a much higher molar mass has stronger intermolecular forces. Why? Higher molar mass, more electrons, more polarizable. Well, this is going to give our iodine the stronger IMFs and carbon dioxide the weaker IMFs. Now remember, we're looking for which substance would naturally occur as a gas. Well, it's got to be the one with the weaker IMFs. It's got to be CO2, which we would have guessed anyway, because after all, we all know that CO2 is a naturally occurring gas. What about iodine? What is the naturally occurring state of iodine? Anybody? Well, it turns out with those stronger IMFs, iodine naturally occurs as a solid. It's a solid at room temperature and pressure. And I'm just going to draw a little sort of squiggly line to make sure we separate the first example from the second example. Okay, great. So we've taken a look to see how there is a correlation between IMF strength and the naturally occurring state of a particular covalent substance. Well, now we're going to take a short look at, well, maybe not so short, but now we're going to take a look at what happens when a substance undergoes a change of state, also called a phase change. Well, it turns out the main thing that happens when substances undergo a phase change is simple, and that is that the separation between the molecules changes. I'm going to highlight that. So when substances undergo a change of state, the separation between the molecules changes. So we can see in the diagram below, all right, each little circle, little blue circle, represents a molecule. And in the solid, they're very close together. Now, the liquids, the molecules haven't changed. The little circles are the same, but what's changed is how far apart they are in the liquid state, and of course, much, much further apart in the gaseous state. So all that's changing is how close or how far apart the particles are. But the individual molecules of the substance don't change. They remain intact. So I'm going to also highlight that. The molecules themselves remain intact. There we go. So let's take a look at the processes of converting solid to liquid to gas and back again in a little more detail. So let's start with the solid to liquid change. Well, the solid to liquid change, of course, is called melting. And when we convert a solid to a liquid, we have to add heat to melt a liquid, which means that add heat to melt a solid, which means that the conversion of a solid to a liquid is an endothermic process. Okay. Now, once we have a liquid, we can convert a liquid to a gas via the process of vaporization. As it turns out, once again, if we want to vaporize a liquid, we've got to add heat, which means that this too is an endothermic process. Now, processes that are endothermic in one direction must be exothermic in the other direction. So if we have a gas and convert it to a liquid, let's remember this is called condensation. Well, when a gas condenses, heat is released. So I'm going to put a negative here for heat is being released. And of course, when we release heat, this means condensation is an exothermic process. And once we have our liquid, if we want to convert our liquid to a solid, well, of course, this is the process of freezing. And, well, to freeze a liquid, we need to get the heat out. We need to get the heat out. So we remove heat. It's negative heat. Heat has to be released. And again, this is an exothermic process. Now, it turns out the amount of heat involved in the conversion of a solid to a liquid or a liquid to a solid has a special name. It is called the heat of fusion. The heat of fusion. So over here, this is called the heat of fusion. And it's given the symbol delta H subscript FUS. That does not look like a U. I'm going to do that again to make sure it's clear. FUS. And it's typically given in units of kilojoules per mole. So what is the heat of fusion? Well, it depends on which direction we're going in. So delta H fusion could either be a positive quantity or a negative quantity. It's positive if we are melting. It's negative if we're freezing. So we could think of delta H fusion, the heat of fusion, to be either the heat required to melt a mole of a solid, or we could think of it as the heat released when we freeze a mole of the liquid. Either one would be fine. Now, the process of going from liquid to gas or back gas to liquid, well, the heat involved in this process here is called the heat of vaporization. Heat of vaporization. And we would use the symbol delta H with the subscript VAP delta H of vap for heat of vaporization, and again measured typically in units of kilojoules per mole. Now, once again, delta H vaporization could be positive or negative depending on whether we are vaporizing or condensing. And so we could consider the enthalpy of vaporization to either be the heat required to vaporize a mole of liquid, or the heat released when we condense a mole of gas. So either which way, it does not matter. Now, one of the things you may have noticed when I put this diagram together is that I've got much longer arrows going from the liquid to the gas state than I do going from the solid to the liquid state. Now, why is that? Well, the reason why, because we're thinking about the process with respect to the amount of heat involved. And it turns out that for all substances, the heat of fusion will always be less than the heat of vaporization, meaning we always need less heat to convert a solid to a liquid. We always need more heat to convert a liquid to a gas. So I'm going to note that over here. So always delta H fusion is less than delta H vaporization. Now you might wonder, why is the amount of heat required to convert a solid to a liquid less than the amount of heat required to convert a liquid to a gas? Well, the answer lies in what is that heat being used for? And the answer is the heat is being used to separate the molecules. Now, if we look at the molecules of a solid and the molecules of a liquid, do we have to do a lot of separation or a little bit of separation? Well, the answer is we only have to do a little bit of separation to get from the solid state to the liquid state. So we don't need a whole lot of heat to pull them apart, just a little bit. And that's what this value is all about. So I should say we need less heat to separate the solid to liquid molecules. But when we are trying to go from the liquid state to a gas state, we have to take those liquid molecules and separate them by tremendous differences to finally get them far apart enough to have a gas. So we're going to need a lot more heat to separate the molecules of a liquid to a gas than we did to separate the molecules of a solid into a liquid. So over here, need more heat, all right, because we have to do much more separation, all right, because more separation of molecules is required for the liquid to gas change. So it's all about the spacings. Tiny bit of separation for the molecules going from the solid to liquid state, but a lot of separation is required to get from the liquid to the gas state. Okay, now what is the role of intermolecular forces on phase changes of state? Because let's remember, this whole topic is related back to the effect of intermolecular forces. Okay, well, I'm going to just scroll up so that we can take a look at that. Well, let's suppose we have a substance that has strong intermolecular forces. Well, if a substance has strong molecular forces, the molecules in that substance will be strongly attracted to each other. Now, if they're strongly attracted to each other, are those molecules going to be easier to separate or harder to separate? Well, the answer is they're going to be harder to separate if they're strongly attracted. And so that's our first statement here. Molecules will be more strongly attracted to each other and harder to separate in substances with stronger IMFs. Now, when we change the state, we're separating the molecules. And so thus to separate them, either from solid to liquid or from liquid to gas, well, if we have stronger IMFs and they're harder to separate, we're going to need more heat to separate them. And not only do we need more heat to separate those molecules, we're going to need higher temperatures to pull apart those molecules that are very strongly attracted to each other. In other words, we could say that as IMF strength increases in a substance, well, what's going to happen is that we're going to need more heat to separate the molecules. More heat, well, the heat is in the form of the heat of vaporization and the heat of fusion. And so the heat of fusion and the heat of vaporization are going to be higher in that substance because we need more heat to separate those molecules. And not only do we need more heat, thus higher delta H fusion, higher delta H vaporization, we need higher temperatures. Well, what kind of temperatures am I talking about? Well, a solid is converted to a liquid at its melting point, and a liquid is converted to a gas at its boiling point. And so we're also going to see that as intermolecular force strength increases, the melting point and the boiling point of a substance will also be increased as well. So this I'm going to sort of circle and star before we do our example to show how this can be analyzed. Okay, so again, IMFs getting stronger. If they're stronger in a substance, particles harder to separate, which means we need more heat to separate them, and we need higher temperatures to separate them. So to illustrate this, well, the example I have here is going to be comparing two substances. The first is ammonia, and the second is methane. So let's write that here. Ammonia. You know what? I need to move that down a little bit. I'm not going to have space. Space, the final frontier. Here we go. So our first molecule is ammonia, and our second molecule is methane. So let's take a look at these two substances and decide maybe which of these would have the higher or lower melting point, boiling point, heat of fusion, or heat of vaporization. And if we want to do that, where do we begin? We begin by analyzing whether they're polar or not, superpolar or regular polar, what their IMFs are, and how strong their IMFs are. So let's begin with ammonia. Well, we've seen ammonia before. Ammonia, of course, is polar. It's also got NH bonds, which makes ammonia superpolar. Meanwhile, methane on the other side isn't polar at all. All of the bond polarities cancel out, and it is a non-polar molecule. Now, superpolar ammonia has both hydrogen bonding and London dispersion intermolecular forces, while nonpolar methane has London dispersion forces only. We're going to remember from our previous section that if the molar masses are similar, we can do a direct comparison of IMF strength. And as it turns out, the molar masses of these two substances are very similar. So the molar mass of ammonia is approximately 17 grams per mole. Meanwhile, the molar mass of methane is approximately 16 grams per mole. So they have similar molar masses. Similar molar masses mean that we can do a direct comparison, and that means that the one with hydrogen bonding has stronger IMFs, which is our ammonia, and the weaker IMFs go to our methane. Now, with stronger IMFs, we would expect the molecules of ammonia to be harder to separate than the molecules of methane. And if the molecules of ammonia are harder to separate, more heat is required and higher temperatures are required to separate those molecules. And so we would expect ammonia to have higher enthalpies of fusion, enthalpies of vaporization, melting point, and boiling point. And if we actually look up the data, we see that this is actually the case. So I did that. I looked up all those values. And I found out that the enthalpy of fusion for both of these substances is, and I have to find the numbers on my paper, 5.7 kilojoules per mole for ammonia versus much lower, 0.9 kilojoules per mole for methane. So more heat required to melt ammonia. Why? Harder to separate the molecule, so more heat. I also took a look at the enthalpy of vaporization for these two substances. And for ammonia, it was 23.4 kilojoules per mole, whereas in methane, I got 8.2 kilojoules per mole. So again, ammonia with the stronger IMFs mean that we need a lot more heat to convert liquid to gas to separate those molecules. I also looked up the melting point of these two substances. The melting point of ammonia is 195 Kelvin, whereas the melting point of methane is 91 Kelvin. So higher temperatures required to melt ammonia. Why? Harder to separate the molecules due to those strong IMFs. And last but not least, I looked up the boiling points of these two substances. The boiling point of methane, 240 Kelvin versus just 112 Kelvin for methane. So in all instances, ammonia with the stronger IMFs has the higher enthalpies of vaporization, fusion, boiling point, and melting point, needing more heat to separate the molecules, needing higher temperatures to separate the molecules. Okay, so now that we've seen how IMFs correlate to the key aspects of phase changes, we're going to take a look at something called a heating curve. Now, a heating curve is essentially a graph. It's actually not curved at all. It's a misnomer. It's a graph that represents how the temperature of a substance changes and how it undergoes phase changes as we continually add heat to that substance. So I'm going to just move this up. Or maybe I'm not. There it goes. We finally got it to move up. So let's talk about heating curves. A heating curve graphically represents the rise in temperature and the phase changes a substance undergoes as heat is added to it. Okay, so I have my axes, my x-axis and y-axis here. Typically, what we see on our y-axis is temperature. This is our temperature axis. Meanwhile, our x-axis is our axis for heat. And you might want to leave a little space before you write heat, because we're going to be writing something above this later on. So I'm going to say this represents the amount of heat that gets added. Now, let's suppose we have some substance at a low initial temperature. Well, at a low initial temperature, that substance is most likely to be in the solid state, So we're going to start down here at some low initial temperature. So let's assume that we have a solid. Now, let's suppose we start adding heat to that solid. If we add heat to the solid, what's going to happen to the temperature of the solid? Well, what's going to happen to the temperature of the solid is it's going to gradually rise. Rise. Now, is the temperature going to rise forever? Well, that's a good question. Well, first of all, why is the temperature rising? Well, the heat that you're adding is going to now increase the kinetic energy of the molecules of the solid. They're moving faster, and those faster moving particles are interpreted by us macroscopically as a rise in temperature. So, all right, we're increasing kinetic energy. The temperature is going up. But interestingly enough, so let's just note that this is our solid right here. So we're heating up our solid over here. Now you might think this line would go up, 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 up as we keep adding heat, the temperature keeps rising, but that's not what happens at all. Instead, something interesting happens. At at some point, the temperature stops rising, even though we keep adding more heat. And what we see is there is a flat plateau. Flattens off for a while. Now, what's going on over here? Well, it turns out this plateau represents an important change the solid is undergoing. It represents the point at which the solid begins to convert into a liquid. In other words, a phase change is happening here. Now, why is the temperature staying constant for the phase change? Why isn't the heat causing the temperature to keep rising? Well, it's because the heat that we're adding to our solid isn't increasing the kinetic energy of the particles anymore. Instead, during a phase change, the added heat is overcoming the intermolecular forces and pulling the particles apart. That's what the heat is being used for. Now, eventually, you add enough heat and the entire solid has converted to liquid. So now at this point over here, we have liquid. We have liquid. So now that we have liquid, if we continue to add heat, well, what's going to happen? Well, if we add heat to the liquid, the temperature starts rising again. Oops. I'm going to try and do that a little bit more neatly. There we go. I'm trying to do this freehand, and it's not so easy, but I'm doing my best. I'm doing my best, folks. Okay, rise, 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 rise. Okay. Now, once again, all right, the temperature is rising because the heat being added to the liquid, let's note that this represents the heat being added to the liquid, is increasing the speed of the particles, their kinetic energy, and thus the temperature of the liquid is rising, rising, rising. But again, eventually, the liquid will get to some temperature at which it now is going to start to vaporize or boil. And so once the liquid starts to convert into a gas, we get another flat plateau. Where this plateau, oops, that's not the most perfect line. Let's see if I can't do that a little bit better. Again, freehanding, doing the best I can, folks. Oh, that's even worse. That's why you should never try it a second time. It's like changing answers on a multiple choice test. Stick with your first answer. All right, that's not so bad. Okay, there we go. So we get another flat line over here, another flat plateau, and this represents the phase change of our liquid into a gas, Now, notice that I made this plateau, this flat line, for the liquid to gas longer than the flat line I used for the solid to liquid. And, well, why is that? Well, this line for liquid to gas, all right, is the heat added that represents the heat of vaporization. And we always know it takes more heat to vaporize than it takes to melt. Why? Because we're pulling the particles much, much further apart when we go from liquid to gas. We don't need to pull the particles as far apart when we go from the solid to liquid state, and so we need less heat. Now, eventually, your entire liquid sample is converted to a gas. And once you have the gaseous state of matter, well, if you add heat to the gas, what's going to happen? Well, all that's going to happen is the temperature starts to rise. And it'll keep rising and rising and rising until you get to whatever final temperature you want your gas to be at. And so this here represents the heating of your gas. Okay. Now I'm going to note some other important things on this diagram, and we're going to be adding things to this diagram as I go along. First of all, when our solid converts to a liquid, the temperature over here on this axis, at which the solid converts to a liquid, well, that's the melting point of our solid. Whereas when the liquid over here is, oh boy, this is going to be hard for me to freehand, converts to A gas, well, that temperature is the boiling point of our liquid. Now, I should also know that this diagram is what we get if heat is added. So if heat is added, we're going up, up, cross, up, okay, and this is the direction we're going in. But we could also think of this diagram as what would happen if heat was removed. Well, if we started at a high temperature with the gas and we removed heat, if we remove heat, the gas cools down and its temperature drops. And then when its temperature drops enough, we get to the point where the gas condenses and converts to a liquid. And so this could be either gas to liquid or liquid to gas here. And then once the gas has converted to a liquid, if we continue to remove heat, the liquid cools, 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 cools. But as we continue to remove heat, we then start to convert the liquid to a solid. So I'm going to put another arrow here in the other direction. And as we continue to cool, all right, we eventually have nothing but solid, and we can then lower the temperature of our solid by continually removing heat. So we can either go in one direction or the other direction. So I should note that where we see the slopes going up, all right, those are the points where we have just the pure state by itself. Over here, just the pure solid, then the pure liquid, and then the pure gas. But in the phase change sections at the plateaus, we have a mixture of two states. So our first phase change at the melting point, solid to liquid, it's a mixture of solid and liquid. Because at first we have a lot of solid and a little liquid. And then as more solid melts, we have less solid and more liquid and less solid until we have nothing but liquid at this point here. And it's the same thing for the vaporization process. For the vaporization, we start with a lot of liquid and a tiny bit of gas. And gradually we're making more and more gas and less liquid. So we always have a mixture of the liquid and gas as we do the phase change until the phase change is complete. Now, some of the things I talked about as I drew this diagram are written out for you on the next page. So let's see what we have here. It says, when heat is added to the pure solid or liquid or gas, the kinetic energy of the molecules increases, which means the particles move faster, and of course, the temperature increases. And that's that upward slope. That's the upward slopes we're seeing for the pure solid, pure liquid, or pure gas. Now, one of the things we can actually do is we can calculate how much heat is required to raise the temperature of each of the pure solid or the pure liquid or the gas. And how do we do that? Well, we're going to use an old friend of ours, an equation that's an old friend of ours, and that is Q equals mc delta T. Yay! For all good old Q equals mc delta T. Let's come back just to give you a last hello in the course. Now, we have to be very careful about the value of C that we use. So C is the specific heat capacity of our substance. And as it turns out, the specific heat capacity of the solid state of matter is typically different from the specific heat capacity of the liquid state or the gas state. And so I'm going to note that we're going to need a different value for each state of matter. So we want to be careful about which value we use, and it's going to change depending on whether we're heating the solid or the liquid or the gas. Okay. Now, I also noted that in our diagram, the plateaus, which are the flat parts of our diagram, mark the phase changes. And we know that the temperature remains constant during phase changes, and that's because the added heat is used to overcome those IMFs and pull apart, separate the molecules. Now, we can calculate just how much heat is required to perform a phase change, convert either solid to liquid or liquid to gas using one of two equations. The first equation is Q is equal to N, which is moles of substance, times delta H fusion. And we would use this equation when we are converting a solid to a liquid or a liquid to gas. Or we would use Q equals moles of our substance times delta H vap if we want to calculate the amount of heat required for our liquid to gas phase change or our gas to liquid phase change. So these are other two important equations that we are going to be associating with a heat curve. In fact, I'm going to go back to our heat curve now. I'm going to pull this back here. So let's suppose we want to figure out how much heat is required to heat our solid from its initial low temperature, that's supposed to be a bracket, and that came out horribly, to how much heat is required to go from whatever low initial temperature our solid starts at up to its melting point. Well, what equation would we use? Well, we would use good old Q equals mass of the solid times the specific heat capacity of the solid times delta T of the solid. And that's how we would calculate the amount of heat we would need to add to get from our low temperature up to the melting point of the solid. Now, if we then wanted to calculate the amount of heat for the phase change solid to liquid, well, what would we use? We would have to take moles of our solid and multiply it by delta H fusion. And that's how we would calculate the amount of heat that we would need to add to completely convert our solid into the liquid state. Now, once we have our liquid, we could then work out how much heat is required to change the temperature of our liquid from its melting point up to its boiling point. So in other words, we could figure out how much heat to go from here to here. And what would we use here? Well, we would multiply the mass of our liquid times the specific heat capacity of the liquid times delta T of our liquid. And that's how we would figure out how much heat it's going to take to go from the melting point to the boiling point of the liquid. If we want to then work out how much heat is required to vaporize the liquid, we would use N times delta H vaporization. And finally, if we have a gas at the boiling point and we wanted to heat up the gas to some final high temperature, well, to do that, we would use M times the specific heat capacity of the gas times the change in temperature of the gas to figure this out over here, how much heat would be required for this process. Okay, wow. So I know this lecture is going on a little bit long, but we're almost done. Let's do an example to illustrate how we can do a calculation involving a heat curve such as this one. So I'm going to scroll back, and let's take a look at number 3 for our ice problems here. It says, given the data below for H2O, calculate the total amount of heat required in kilojoules to completely convert 30 grams of solid ice at negative 15 degrees Celsius to steam, aka water vapor, at 125 degrees Celsius. And we're given some data for water. Its melting point, its boiling point, heat of fusion, heat of vaporization, and we're also given the specific heat capacity values for the 3 states of water: ice, water, and steam. Okay, so how are we going to do this? We're going to break this down into sections. Note that we're starting with solid ice at negative 15 degrees Celsius. So the first thing we're going to need to do is to raise the temperature of the ice. Now, how high can we raise the temperature of the ice before it melts? Well, the highest we can go is 0 degrees Celsius, because once we hit 0, it starts to melt. And so our first step in this calculation would simply be to heat the ice from negative 15 up to 0 degrees Celsius. So that's the first thing we need to do. Oops, let's get that right. From 15 to 0 degrees Celsius. So we're going to be heating the pure solid. And if we're heating the pure solid, we're going to be using Q equals M, specific heat capacity of the solid, times delta T. Well, the mass of our sample is 30 grams. And the specific heat capacity of the solid state, which ice is the solid state, is over here. It's given to us in our data set as 2.09 joules per gram per degree Celsius. And now we need delta T. Well, here's T initial, here's T final. The difference between T initial and T final, that's an easy one to do in our heads, is 15 degrees Celsius. That's the temperature change. And when we plug and chug, I ended up getting, what did I end up getting? I ended up getting 940.5 joules. But, you know, we want our answer in kilojoules, and it looks like I need 3 sig figs. So if I convert this to kilojoules to 3 sig figs, I get 0.941 kilojoules to take our ice from negative 15 to 0 degrees Celsius. Okay, so what's going to happen next? Well, the next thing is we now have our ice at 0 degrees Celsius. So any heat that's added once we hit 0 degrees Celsius means we're melting the ice. And so our next step is to melt the ice at 0 degrees Celsius, because that's what happens when we get to the melting point. And so what we're doing here is the solid to liquid conversion. Now, this is a phase change. And so for this phase change, we're going to have to use Q equals N delta H fusion. So we need moles, not mass. So the mass of our sample is 30 grams. So we're going to convert 30 grams to moles. Well, this is H2O, so it's 1 mole per 18, roughly 18 grams. That gets us moles. And we're going to multiply this by the enthalpy of fusion given to us with our data set, which is 6.01 kilojoules per mole. So grams cancel grams, moles cancel moles. We're going to get the amount of heat needed to melt our ice in kilojoules. And I ended up, and do check my math, I get 10.0 kilojoules. I hope I did all the math correctly, but hopefully one of you will correct me if I'm wrong. Okay, so now we've melted our ice. What's the next step? Well, now, if we've melted the ice, what do we have? We have liquid water at this point. We have liquid water at 0 degrees Celsius. So now we're going to heat the liquid water from 0 degrees Celsius up to, well, how high can we heat it? Well, the highest we can heat the water to is 100 degrees Celsius. We can't go any higher than that because it's going to turn into steam, right? And so now we're going to be heating our water. And we're going to start off at our low temperature of 0 and heat it up to the high temperature of 100 degrees Celsius. Okay, so now we're going to be using good old Q equals MC delta T. But this time C is the specific heat capacity of the liquid state. And if we plug and chug, that's 30 grams of water, because mass is constant, mass doesn't change. And our specific heat capacity of water, good old 4.184 joules per gram per degree Celsius. And 0 to 100 means we have a temperature change of 100 degrees Celsius. And I did my plugging and my chugging, and I got 12,552 joules. And if I write this to 3 sig figs and convert to kilojoules, this would be 12.6 kilojoules. Okay, so now I've got water at 100 degrees Celsius. If I add any more heat to the water at 100 degrees Celsius, what happens? It starts to vaporize. And so now we're going to vaporize the water at 100 degrees Celsius, which is its boiling point. So vaporize water at 100 degrees Celsius. So we're doing a phase change, which is the liquid to gas phase change. So what do we need for the liquid to gas phase change? Q equals N delta H vap. So we've got our 30 grams. We're going to convert that to moles using the molar mass of H2O. And now we're going to multiply that by the enthalpy of vaporization, which has been supplied to us as 40.63 kilojoules per mole. Grams cancel grams, moles cancel moles. We get our answer in kilojoules. Into 3 sig figs, I got 67.6 kilojoules. Oof, okay, we're almost there. So now we've vaporized the water. So what do we have now? We have steam. We have water vapor. And what temperature is our steam at? It's at 100 degrees Celsius. So now we're going to take our steam and heat it from 100 degrees Celsius to what? Oh, well, that's right here in the problem. We want to heat it up to 125 degrees Celsius. So we started at -15, and we're going to end at 125. So we're going to now heat the steam from 100 to 125 degrees Celsius. And I will note that we started here and we're ending here. Now, our last phase requires Q equals MC of the gas times delta T, 30 grams times, let's see, our specific heat capacity of the gas, 2.03 joules per gram per degree Celsius, times our temperature change, 100 to 125 is just 25 degrees Celsius. And in the end, I got 1522.5 joules, which is identical to 1.52 kilojoules to 3 sig figs. So we want the total amount of heat for the entire process. So if we want the total amount of heat, what are we going to do? Well, we're going to add up all the heats that we calculated. This one, let's call this one, here, let's name these heats. Let's call this heat here Q1, this heat here Q2, Q3, Q4 for each of the 5 processes, and Q5. What we're going to do is add them up. And when we add them up, we're going to get the total amount of heat required. So I have just enough space to squeeze that in. So total heat, here I'll put a little star beside this, required, equals Q1 plus Q2 plus Q3 plus Q4 plus Q5. And I actually added them up a little bit earlier. Looks like we're going to report our answer to 1 decimal place when we do the addition, and I ended up getting 92.7 kilojoules is the total heat required to go all the way from ice at -15 all the way up to steam at 125 degrees Celsius. Wow, my fingers hurt. Now let's just put our little box around our final answer. Okay. Now, let's take a very quick look at number 4. Turns out I'm not going to work out number 4, but you are. I want you to work it out yourself. So number 4 is very much related to number 3. Number 4 for our ice examples here says, suppose 18.5 kilojoules of heat is added to 30 grams of ice at 0 degrees Celsius. The question is, what will be the final state and temperature of the sample? Final state and temperature. So when we put the heat into that 30 grams of ice at 0 degrees, what's going to happen? Is the temperature going to change? Is there going to be a phase change? So this is what I'd like you to figure out. And it should be very easy because you did the hard work in number 3. You already did the hard work in number 3. So I'm going to actually give you the answer. I'm going to give you the answer, but I want you to be able to work this out by yourself. And so the answer to this question is that the final state of our sample is going to be as liquid water. That's our final state. And the temperature that we're going to find the water at after adding 18.5 kilojoules of heat to the 30 grams of ice, I worked out as 67.7 degrees Celsius. And I'd like you to try working this out on your own. And if you're stuck and don't know how to do this, bring it to me during office hours, and we will work on this together. Okay, so we're done talking about phase changes, states of matter, and how intermolecular forces are related to all of this. Whew, my fingers hurt. All right, good point. Good thing that we're ending the lecture now. So everybody, you take care, and I'll be talking to you again very soon. Bye now.